in exactly the same manner as the system of integer behaves. So that is the identification. So because of this, we will now identify each integer a with the rational number a by 1. That is, we will see no essential difference between a and a by 1. The above identities guarantee that the arithmetic of the rational numbers is consistent with the arithmetic of the integers. As far as integers are concerned, if we are thinking of them as being a part of the system of rational numbers, not only are these things just simply a matter of writing, instead of writing a by 1 we are writing a, but that is not the only thing. The arithmetic also stays consistent. Whether you write a by 1 and b by 1 or you don't write that by 1 part, it does not matter because of these identities. Thus, just as we embedded the natural numbers in the integer, for now you interpret this word embedded in the usual literary sense, but this word embedded or embedding has a precise mathematical sense, which is also not something different from the literary sense. It's that same thing. It's like a way of identifying a given system as a subsystem of another system, although it may not be exactly a subsystem, but it behaves like a subsystem of that other system, which has no essential difference with this original system. So embedded the natural numbers inside the integers we now embed the integers inside the rational numbers. In particular, okay, I am writing from here. I don't want to miss these lines that the author has written, so he is dragging this thing on, but let's just see what he has to say. So in particular, all natural numbers are also rational. So this has come from a double embedding. First, natural numbers are identified as integers, and then that integer is identified as a rational number. For instance, zero is the rational number 0 by 1, and 1 is the rational number 1 by 1. Okay. Now the time has come for us to define an equivalent of the operation of negation in the set of integers for the set of rational numbers. Here also we will define something just like negation. If you remember, negation is something that is opposite to addition. It creates a situation for us to define subtraction. So we want to define an operation that corresponds to negation for rational numbers that will eventually allow us to define division, actual division, and you can guess what that operation will be: reciprocal. So we now define a new operation on the rationals. Reciprocal. Let x equal to a by b be a rational number different from 0. Oh, I should have said one more thing before writing this, no? Okay, let me just simply say it. Suppose x is 0, such a rational number. Forget this condition. X equal to a by b is a rational number. Suppose x is 0. That means what? A by b is equal to 0, and 0 is nothing but 0 by 1. So from the definition of equality of two rational numbers, this gives us a times 1 is equal to 0 times b, or b times 0, or a is equal to 0. Conversely, if a is 0, then we have this gives us this, and this gives us this. That means the rational number x is 0 if and only if a is equal to 0, or equivalently x is non-zero if and only if a is non-zero. Okay, so if a rational number is non-zero, its first component has to be non-zero. and conversely, if the first component is non-zero, the rational number is non-zero. So here it is given that the rational number is different from 0. This implies A is not equal to 0. Okay. The reciprocal x inverse of x is defined by this equation or this formula. X inverse is just b by a. Note that this formula makes sense because a is non-zero, so this is a legitimate rational number. In fact, we can write that, note that since a is non-zero, b is also non-zero, that is there, it comes from the definition of this rational number itself, but additionally a is also non-zero. Since a is non-zero, b by a is a legitimate rational number. We wrap this part off because we have already seen how it happens that a is non-zero. Okay. But this is also a new definition, just like the negation was, and one has to prove that it is well defined in the same sense that we proved addition, multiplication and negation are well defined. Okay. And this I am not going to do. One can verify that this operation is well defined. You take two rational numbers a by b and a prime by b prime, assume that they are equal and show that their reciprocals are also equal. That is, the reciprocals of two equal rational numbers are also equal. In bracket I write verify. Okay, so this is left to you. However, in contrast, an operation such as the numerator of, see, this is the place where we will see that we can't say the numerator of a rational number. So if an operation allows us to define the numerator of a rational number, that is not well defined. Is not well defined. The rational numbers, and the reason is this. The rational numbers 3 by 4 and 6 by 8 are equal, but their denominators oh sorry, not denominator, what the hell, numerators. What we ordinarily know as the numerator of an expression. When we have an expression of the form a by b, then we can say its numerator. Okay, but when we say rational number, because it has infinitely many different types of expressions, so we cannot say numerator. But there numerators 3 and 6 are not, they are not equal. Okay. And keep in mind that we have defined reciprocal of a rational number, all rational numbers that are different from 0. For 0 we do not define a reciprocal, and which has to do with the fact that we cannot divide by 0, since reciprocal ultimately will lead us to the definition of division of two rational numbers. So we cannot divide by 0. We however leave the reciprocal of 0 undefined. There is no meaning for us of the reciprocal of 0. Okay, so now we have come to, having seen all these things, we have now come to the laws of algebra for rationals, just like we had laws of algebra for integers. So this is proposition 424. What was 423? Item 423. Have I missed anything? Now item 423 was the lemma that the operations addition, multiplication and negation are well defined. Okay, fine. So this is laws of algebra for rationals. Let x, y and z be rational numbers, then the following identities hold. And we will see that majority of these identities are identities we have already seen for integers, but now they are being stated for rational numbers. So they are not exactly the same thing, although they will look exactly the same. Addition of rational numbers is commutative. Addition of rational numbers is associative. X plus y plus z. There is an identity element or zero element. Every rational number has an additive inverse, which is its negation. Keep in mind that we have already defined negation. And if we add the negation of a rational number to the rational number in any order, we get that number 0. Okay, then we turn to multiplication. We have stated all the things for addition, which involve only addition. Then multiplication, just like addition, is commutative. multiplication is associative, there exists a multiplicative identity 1. So these are the properties of multiplication. And then the distributive laws which combine addition and multiplication. The left distributive law, x times y plus z is equal to xy plus xz, and the right distributive law. But there is one more, and that's why rational numbers are different from the integers in that sense, in this algebraic sense. Additionally, if x is not equal to 0, then we have already seen that there is something known as its reciprocal, and that has this property. Okay, so just like the corresponding proposition for integers, this is also followed by a remark. This is remark 4 to 5. The above set of 10 identities has a name. They are asserting that the rational numbers, or same thing, it's the set of all rational numbers, form a field this is better than being a commutative ring. Integers form a commutative ring. Rational numbers also form a commutative ring, but it has this extra condition for which it is called a field. Because of the tenth identity. Okay. Note that this proposition supersedes the previous similar proposition for integers. So that is 4,1. What was the number? 416. Okay, now we come to the proof. Here also the full proof will not be done, obviously. So we will only deal with this. Note that I am not writing deal with associativity of addition because we haven't given them any name. That is because we are not trying to study them algebraically as fields or rings. For us, they just have some name, we keep it just like that, because we are not going to look at very many different examples of fields or rings. There are other systems like this which also behave similarly. So that's why we are just going to write it like this without any name. The rest of the identities are left to exercise 6. No, sorry, exercise 3. Like the previous proposition for the integers, this one is also quite easy. You just have to consider the expressions for these rational numbers and calculate the left hand side and right hand side separately and ultimately see that they are equal. So let x be equal to a by b, y be equal to c by d, and z be equal to e by f, where a, b, c are integers, or not a, b, c, sorry, a, c and e are integers and b, d, f are non-zero integers. Then let me carry out the computation here. X plus y plus z, this will be equal to a by b plus c by d plus e by f. So this, first of all, by definition, this is ad plus bc by dd plus e by f. Again, if we apply the definition, this times f, that means adf plus bcf plus this times e, bde divided by this times f, that means bdf. Note that we carelessly used distributive law and everything about the system of integers that we already have proved. Whenever we encounter integers and operations between them, we are going to calculate just how we usually calculate with them, because now we have all the proofs. Okay, so we don't bother anything about that. So let it sit like this, and x plus y plus z is equal to a by b plus c by d plus e by f. So first of all, this gives us CF plus DE by DF. Then for the final one, we have to multiply this with this. That means ADF plus B with this thing, which after applying the left distributive law gives us BCF plus BDE divided by B times DF. Here also, while writing BDF, we are using the fact that multiplication of integers is associative, without which first of all such a product will not make sense, and the second thing is that while calculating this one, we will get BD times F, whereas while calculating this one, we will get B times DF. So associativity of multiplication of integers allows these two things to be equal. Okay, now we match the two expressions ADF, ADF, BCF, BCF and BDE. So that's it. Thus, and we end the proof here. Okay, now we are going to define quotient of two rational numbers, or when one rational number is divided by another rational number, or maybe by itself, what do we get? And we are going to use the reciprocal, the operation reciprocal for doing that, just like how we defined subtraction using negation. For rational numbers x and y, where y is not equal to 0, we define their quotient x by y by the following formula. X divided by y is defined to be the product of x and y inverse, that means reciprocal of y. Okay, now having this definition, we are now in a position to get rid of that meaningless symbol that we have been using so far, not this one, in the expression for a rational number. Note that if a and b are integers where b is non-zero, then a divided by b. How will you make sense of this? This can be, this should be interpreted as saying that this is the quotient of two rational numbers, because you see we have defined quotient only for two rational numbers where the second one is non-zero. So this is a quotient of two rational numbers where this integer a itself is a rational number. It's the rational number a divided by 1, and b is the rational number b divided by 1. We have already seen that a by 1 is equal to 0 if and only if a is equal to 0. So the fact that b is a non-zero integer tells us that this is also non-zero, this rational number is also non-zero. So from that identification, this actually means a by 1 the quotient of a by 1 and b by 1. Then you apply the definition of quotient, that is the product of a by 1 and the reciprocal of b by 1. And reciprocal of b by 1 can be formed, or it exists because b by 1 is a non-zero rational number, and the reciprocal is this 1 by b. Now you apply the definition of product of two rational numbers. A times 1, this is a, and 1 times b, this is b. So you see that taking everything into consideration, this symbol is actually equal to the quotient of a and b. Of course, but before having these things, we could not have written just like this. I mean, in the beginning itself, that would be circular. So we can now discard the symbol this and use the more familiar one, a single slash in writing a rational number. So our building has now been constructed. We are getting rid of the scaffolding. So proposition four to 4 allows us to use all the normal rules